Now, let us discuss a case of when we use the Kolmogorov-Smirnov test but for discrete distributions. Suppose we use a binomial distribution or a geometric distribution or any other discrete distributions. So ito yung mga remarks or idea na helpful dito. So, for discontinuous cases, asymptotic distributions of the test statistic can be obtained but with some undesirable properties. Conover derives a method for finding the exact critical level, which is approximate in the two-sided case of the Kolmogorov-Smirnov one-sample test statistic when the hypothesized distribution function is not continuous, which is also appropriate when the sample case is 30 or less. So, in essence, meron naman tayong way, pero hindi lang talaga siya ganun ka-significant yung magiging results because the Kolmogorov-Smirnov test is mainly used for continuous distributions. Next, suppose we want to test certain distributions, say normal or exponential, but with unknown parameters. Dito na natin magamit yung Lilliefors'S test. Now, let us discuss the Lilliefors'S test for normality with mu and or sigma unknown. In this test, we consider the problem of a goodness of fit test for the normal distribution with no specified mean and variance. The problem is very important in practice because the assumptions of a general normal distribution with the known mu and or sigma is necessary to so many classical statistical inference procedures. We will have three cases for this, pero let us focus on the first case muna, which is if both mu and sigma are unknown. For our hypothesis to be tested, our null hypothesis will be the data is normally distributed with mu and sigma squared unknown, and for our alternative hypothesis, the data is not normally distributed. For the test statistic naman, essentially same lang siya sa before na one sample case, but dito iba na yung magiging way natin to compute f null of x. So in this case, f null of x is computed as the cumulative standard normal distribution cat phi of z, where z is equals to x minus x bar over s for each observed x. X bar is the mean of the sample n observations, and s squared is the unbiased estimator for sigma squared, which is computed with n minus 1 in the denominator. So since there are parameters are unknown nga, our way of computing for z will be different kasi for this case, we will have to use some estimators to represent our mu and sigma. We all know that x bar and s squared are unbiased estimators for mu and sigma squared respectively. So for our decision rule, we reject the null hypothesis if d sub n is greater than d n alpha, and we will use table O. For the use of software, the Lilliefors'S test can be performed using the lilly.test function in R. We first must install the NOR-test package. So ito yung example ng syntax. X is a vector of the observations, and we use the code lilly.test of x. Now let us have an example. A random sample of 12 persons are interviewed to estimate median annual gross income in a certain economically depressed town. Use the most appropriate test for the null hypothesis that income data are normally distributed. So, ayan yung given na data and walang in-specify na mean and variance. So, ayan, yung first step natin is define the hypothesis. So, the null hypothesis states that the income data from the economically depressed town came from a normal distribution versus the alternative that the income data from the economically depressed town does not come from a normal distribution. And for our test statistic, same lang siya sa before, which is yung supremum of s of x minus the f null of x. So for our decision rule, we reject each null if d sub n is greater than d n alpha. So we use table O, and ayan nga, makita natin na since Rn is 12 and our level of significance alpha is 0.05, we reject each null if d sub n is greater than 0.242. So for our solution using the manual computation, first we arrange our x's in ascending order. Tapos yung z naman natin computed by x minus x bar, which is 10,400 in this case, tapos over s, which is 2,773.25. Tapos yung s of x naman natin, nakuha na natin siya before, which is yung for the cumulative frequency lang. And yung f null of x, gagamit tayo ng standard normal table para makuha yung value ng cat phi of z. Tapos yung the following columns, which is yung nagawa naman na natin sa previous topic, which is yung si one sample case. So let's have an example. So first, ayan yung x natin, 6,900. Tapos yung z natin, plug in lang natin siya, which is 6,900 minus 10,400 over 2,773.25. So may kita natin na ang value niya is negative 1.26. Since ito yung ni-round off natin siya in 2 decimal places kasi ayun lang yung makikita sa standard normal table. So for s of x, 1 over 12 since 1 pa lang naman yung count dyan, which is equals to 0.0833. Tapos, so f null of x natin, if na-evaluate na natin yung nakuha nating z, which is negative 1.26 sa standard normal table, so ang makuha nating value ay 0.1038. And yung sa next column naman, s of x minus f null of x, so makuha natin siya by subtracting lang nga, gaya nung sa one sample case. So, 0.0833 minus 0.1038, which is equals to 0.0205. So, don't forget na kinukuha natin dito is yung absolute value. So, kaya all dito is positive number. Same goes with the next column. So, equal siya sa 0.1038 kasi kukunin natin yung element before this given row. So, in this case, wala naman. So, 0 sa s of x. Tapos, ima-minus natin siya sa f null of x ng nasa row na yon, which is 0.1038. So, kaya natin nakuha yung 0.1038 dito. So, ayun, apply lang natin siya sa other columns and ayun yung makuha nating values. So, ayan, since kompleto na yung values natin, we can get our test statistic, which is 0.1946. Since if you observe natin sa last two columns, makikita natin na ayun yung greatest value. So since 0.1946 is not greater than 0.242, we do not reject the null hypothesis. Therefore, the income data from the economically depressed town came from a normal distribution at 5% level of significance. So for our p-value, the probability of d sub n is greater than or equal to 1.946 is greater than 0.1 kasi kung titignan natin yung table, makikita natin na yung pinaka-extreme value na doon is for values of d 0.223 is equals to 0.1. So for our software results, ayan, i-run lang natin yung library North test. If hindi nyo pa na-install yung package na yon, install nyo lang siya. So next, define natin yung magiging vector natin, which is in this case yung income. So, ayan. Then, i-run na natin yung lily.test of income. So, ang lalabas dyan na value of d is equals to 0.19541. And yung p-value natin is equals to 0.2331. So, yung d natin, meron lang siyang rounding error since hindi siya ganun ka-exact. So, yung first two decimals naman niya is nagtama. Tapos yung sa p-value natin, we can verify that it is indeed greater than 0.1. So, para makuha naman yung exact value na para magtugma siya sa nakuha natin sa R, kapag gumamit tayo ng software, since dito, ang kanaiban lang niya sa previous way, which is yung manual computation, is that yung z values natin is ni-round na natin siya sa 4 decimal places, which is hindi naman talaga natin siya magagamit if manually nating titignan sa table. So, if ayang 4 decimal places yung kinuha natin yung cat phi niya, ang may makakuha nating f null of x ay iba, which is magiging mas exact. So, ang makuha natin sa last two columns ay mas iba siya compared sa kanina since dito ibang values na yung nakuha natin for z. So, ayun, ang magiging test statistic na natin dito is 0.1954, which we can verify sa next slide na ayun nga yung nakuha ang value ng d sa R. So, tignan naman natin yung other cases ng Lilliefors'S test for normality. So, in this second case, if mu is known and sigma is unknown. So, same lang naman siya sa before. Ang pinagkaiba lang niya is yung way sa pag-compute ng z, which is equals to x minus mu over s. For each observed x, mu is the known mean and s squared is the unbiased estimator for sigma squared computed with n minus 1 in the denominator. So, since mu nga yung known, mapaplug in natin siya sa formula. And sigma is unknown, so gagamitin natin siya ng unbiased estimator na S. And for the decision rule, same lang siya, pero we will look at table A.19b. And for the last and third case naman ng Lilliefors'S test for normality, if sigma is known and mu is unknown. So, magbabago lang ulit siya sa test statistic natin kasi yung z naman natin dito is computed by x minus x bar over sigma. For each observed x bar is the mean of the sample of n observations and sigma squared is the known variance. So, papalitan lang natin yung dito ng x bar kasi i-estimate natin siya since unknown nga siya. And yung sigma squared, mapaplug in natin siya since siya yung known dito. And for the decision rule, same lang siya sa before, pero in this case, we will use table A.19a. So next, let us discuss the Lilliefors'S test for the exponential distribution. So in this test, we consider the problem of a goodness of fit test for the exponential distribution with no specified mean. The assumption of an exponential distribution with an unknown mean is made in many applications, particularly where the random variable under the study is a waiting time, the time to the occurrence of the event. So, for our hypothesis, the null hypothesis states that the data is exponentially distributed with unknown mean, and the alternative states that the data is not exponentially distributed. So, moving forward to our test statistic, it is the same as before, the test statistic D, wherein it is only different with the way we compute f null of x. So, f null of x is computed as 1 minus e raised to the negative x over x bar, or 1 minus e raised to the negative z, wherein z is equals to negative x over x bar. So for our decision rule, we reject h null if t sub n is greater than d and alpha, and for this case, we will use table T. For the use of software, the Lilliefors'S test for the exponential distribution can be performed using the LCKS function in R. We first must install the kscorrect package. So for our syntax, we have LCKS of x, and we define the CDF to be px to denote that it is an exponential distribution. So we will see here that x is a vector of the observations, and CDF is a character string which is used to name our hypothesis cumulative distribution function. Let us now have an example. Test the null hypothesis that the data below arose from a one-parameter exponential distribution. So the data is as follows. Now let us define our hypothesis for this problem. So our null hypothesis states that the data is exponentially distributed with a known mean versus our alternative that the data is not exponentially distributed. Now for our test statistic, since the test is two-sided, we obtain the test statistic by as follows. So next, for our decision rule, we reject h null if d sub n is greater than d and alpha, and we use table T. So in this case, we can see that n is equals to 10 and our significance level is 0.05. So we will reject h null if d sub n is greater than 0.325. So for our solution, first, we arrange our x's in ascending order and we define our z to be z is equals to x over x bar, where in this case, it is equals to 5.68. So same lang yung pagkaka-define sa ating s of x. And for our f null of x, since ito yung sa CDF na exponential, we define it as 1 minus e raised to the negative z. And yung susunod na dalawang columns ay same lang sa pagkaka-define natin before. So let us have an example. Try natin yung x is equals to 1.5. So for our z, so yung z natin dyan is equals to 1.5 over 5.68. And yung s of x natin is 1 over 10, kaya 0.1 siya. Tapos yung ating f null of x is equals to 1 minus e raised to the negative 0.2641, which is equals to 0.2321. So, ayun yung way kung paano natin siya nakuha. And yung sa next two columns naman, same lang siya sa before, yung sinusubtract lang. So, 0.1321 and 0.2321. So, ayan, gayahin lang natin siya so for all the values of x, and we can conclude na yung ating magiging test statistic is 0.2330 kasi ayun yung maximum or yung greatest value doon sa dalawang columns na nasa huli. And our conclusion would be, since d sub n is equals to 0.2330 is not greater than 0.325, which is our critical value, we do not reject the null hypothesis. Therefore, we do not have sufficient evidence to state that the data came from an exponential distribution at 5% level of significance. So for our p-value, we get that probability of d greater than 0.2330, which is our test statistic, is greater than 0.1 kasi kung titignan natin yung table, yung pinaka-extreme na doon is equals to 0.1. Yung ating nakuwang test statistic ay nag-exceed pa doon, thus magiging greater than 0.1. So for our software results, we run the library kscorrect and we define our vector expo, which is yung data na nasa given kanina. Then, we use the test lcks expo, which is yung vector natin, and yung CDF natin is yung px kasi nga exponential tong ginagawa natin. So ang lalabas na test statistic d natin dyan is equals to 0.2329762, which is approximately equal naman sa na-compute natin, pero dito is meron lang siyang rounding error. And yung ating makukuhang p-value is equals to 0.3408, which is indeed greater than 0.01.